Okay, please start. So the final speaker of this session is Michael Kao. The title of his talk is Challenge Simulation, Finite Block Length, and Broadcast Challenge. This is joint work with Navenish Ramakrisham, Mario Belta, and Marco Tomameteo. Please start.
Thanks, Dr. Hayashi. Thank everyone for coming to today's talk. So tonight, I'm going to talk about the finite block length channel simulation. My name is Dr. Michael Cao, and this is joint work with Navnis, Mario, and Marco. So the question or the setup is we consider the classical, everything is classical in this talk, unlike the previous two talks. Wait, I didn't even make sure that my voice can be heard. Is it operational? Okay, I just assume it works.
Yes.
Okay, thanks. Okay, so the problem setup is we consider a problem of simulating a target channel, say W. Wait. Then and with the assistance of shared randomness, we're in this diagram. S is a shared randomness, and you have encoder ES and decoder DS, and you map the input to a certain message, and then you decode it. The target is to have your this effective joint distribution to be epsilon close to a certain distribution, where a certain distribution is derived from a specific channel W. And however, the PX is not controlled by you. And what you want is this thing to be small in terms of total variational distance for all input distributions. And wait. So we're interested in finding the smallest alphabet for M, such that there exists some encoder, decoder, and shared randomness tuple satisfying the distance constraints. And that is called the epsilon cost of the task of channel simulation. So this is related to the notion of strong coordination, in which case PX, the input distribution, is actually known beforehand. In that case, you try to reconstruct the joint distribution PXY, where despite knowing the input distribution, but the input distribution symbol is not controlled by you. Whereas in this case, in channel simulation, you need to recover the joint distribution, but you also need to do so without the knowledge of the input distribution in a sort of universal way. Also, the problem of channel simulation and channel coding are kind of dual problem of each other. So the coding problem essentially is using, say, your resource channel W to simulate a perfect channel. You simulate R copy of the perfect channel, where usually I is called the rate of your communication. Then reversely, you could use those number of perfect channels to simulate certain numbers of the original channel. So one thing you can make sure is the ratio, it will be smaller or equal to 1, because you cannot create more resource by not introducing additional resources. Also, this problem is directly related to the reverse Shannon theorem. It is in the case of reverse Shannon theorem, it's actually considering the problem of channel simulation in an asymptotic manner. But in today's talk, we are talking about the one-shot and finite block length situation. So the main results, I'll briefly go through the main results of our work, and then I will only talk about some of them in details. So we have one-shot achievability and converse, which in terms of smooth max information, where the smooth max information we define it in terms of partial smooth max divergence, which is defined in terms as using a max divergence, but you just draw a ball, epsilon ball around the joint distribution, but you fix the px. I mean, that's why it's called partial. And we can see that, I mean, we found that the for a given tolerance epsilon, the log of the minimum message size, you need it at least to be the I max epsilon. And for achievability, we also have an achievability result that you at most only need I max epsilon minus delta plus certain formed terms. Then, shouldn't this be 2 slides? Oh, that's a latex error. So we also have the second order expansion for simulating, say, n copies. Sorry, I'm not sure where the slide number is. Okay, for second order expansion, we consider simulating n copies of the channel DMC W within a TVD of epsilon. In that case, we know the first order term is channel capacity, and the second order terms in terms of square root of n times certain constant, and the constant is in terms of the epsilon channel dispersion. This is very similar to the result of channel coding, the result of second order result of the channel coding. In that case, you will have, this term will be same, and then the second term will be epsilon. But there will be a gap between the channel simulation and channel coding on second order. Therefore, we already know that one will not have channel interconversion on second order if you lose something. In the case when the epsilon channel divergence is strictly larger than 0, we also have a third order upper and lower bounds. They don't match currently, and we are still working on that. So the third order terms is in terms of log n. We know it's between plus and minus log n. Then there's a constant term after it. So we also did the considering situation with moderate deviation errors, where the epsilon, the tolerance we allowed, will tend to 0 exponentially with respect to 2 to the power n a n squared, where a n is a moderate sequence. It tends to 0, but n times a n squared tends to infinity. In this case, we know that the kind of in a similar notion of the second order, you will have the multiplicative constant as square root of 2 to the power v max. Then the remaining will be negligible compared to an. So as a second part of our result, we were able to connect the problem of non-signaling channel simulation to the random assisted channel simulation. In particular, the non-signaling channel simulation cost can be written as a linear program. And we are able to show this linear program will exactly have this solution, which is the I epsilon max. Meaning that non-signaling channel simulation will need the lower bound we see on the last page for the random assist channel simulation. Of course, this also provide a linear program for us to compute the lower bound of the previous page. And in this case, we have some numerics. In this specific figure, we were considering a binary symmetric channel. I forgot the crossover probability. But I remember epsilon is 1/5 in the tolerance. So we were also able to generalize our result to broadcast channels. For the situation with two receivers, this is the diagram on the setup for for the channel simulation. In this case, we have two shared randomness instead of a shared randomness for everyone. That one would be stronger. Of course, that would also work. And the task is also to have the joint distribution to be close. And one is the result of the channel, and the other is the result of your protocol. And you want them to be close regardless of the input distribution and without knowing the input distribution. So we have the inner and outer bound to the simulation region in terms of spectrum divergence. We are defining spectrum divergence slightly different by requiring A to be non-negative. And asymptotically, if you consider as n copies of simulating n copies of broadcast channel, then we consider the rate of such simulation and let epsilon, the tolerance, tend to 0. We end up having the region of the simulation region, a simulation rate region, sorry. And in this case, on the left-hand side, it is an example of a simulation region of degraded binary symmetric channel. It means like you have two binary symmetric channel. You just fit the output of one as an input to the second, and then you have one input and two output, like X, Y1, then Y1 to Y2. And on the right-hand side, it is the simulation region of three binary symmetric channel linked to each other, linked to the other. It is still called degraded binary symmetric channel. So you have X, Y1, then Y1 to Y2, then Y2 to Y3. So this generalized to K-partite broadcast channels, where you will have a similar bound here. Here, C tilde is the supermem over all input distribution of the common information, defined like this. So C tilde in this specific example, C tilde part is responsible for this diagonal cut. So for the technical part of today's talk, I'm only going to talk about the one-shot result and the asymptotic analysis due to time constraints. We are finishing an archive draft. It will be ready soon, at least on the technical part already. So the achievability part first. Achievability part of the result depends on, we use the convex split lemma. We recently realized there are other better, potentially better method. So the convex split lemma, what it says is that if you have a joint distribution over X and Y, and let Q be any, it's important, let Q be any distribution over the output alphabet Y, and given any epsilon and delta, and then if M is large enough, larger than this this value, then if you let J be a uniform distributed among 1 up to M, and condition on J, you have X and M copies of M number of Y distributed like X and YJ, the J's one are distributed according to the joint distribution, and remaining one just copy ID copy of Q. Then this distribution will be very close to the distribution that you have PX, but everybody else is just Q. So you don't necessarily, in the second one here, you don't have the information on on the on Y, the original Y. So what we can use this convex split lemma to cook up a protocol for channel simulation, and it goes like this. So say let px prime y prime be the optimal PMF for Dmax. And in this case, Dmax means that this px prime y prime is close to pxy, and px prime is exactly same as px. And their log likelihood ratio is smaller or equal to this number. Okay, so we can construct random variables j and x prime and all these y's from this x prime and y prime on the as illustrated on the last previous page. So we know that using property of the channel of the information divergence, you can simply write out that the KL divergence between this constructed random variables without j and the situation that all these y's are independent is smaller or equal to this one. This is just a property of KL divergence, which is smaller than this one, which is nothing special. Then here, this is because of the here's because of the previous lemma. Then sorry, actually I'm trying to I confused two slides. This is the earlier slide, so this one is proving the lemma one. Oh, I apologize. So yes, we constructed a random variable like this, then we use the property of the KL divergence, and we can show that they are close. Yes. So using this lemma, the protocol goes like we chose specific Q. Then if it is close, then we can use the previous lemma to show that the constructed J prime up to Y primes, they are close to the target protocol. And the proof goes exactly okay. This is what I have been trying to talk about in the previous minute. Okay, so for the converse, the converse depends on the properties of the max information and its relationships to Dmax and partial smooth Dmax. So to prove the converse, we consider, say, xy to be the distribution generated by the protocol. Then by lockability, we know that first we know that log m equals Imax of x and s. S is the shear randomness and plus log m. This is because log m is simply not here. This part, the Imax x and s is simply 0 because they're not they're independent. Then this is greater or larger than Imax x and ms as a result of lockability. Then using data processing inequality, we can replace ms by y. Then the remaining part is just to expand this Imax and consider a definition of the smooth divergence. Firstly, it is defined, Imax xy is defined like this. This is infimum over Q. Then this is again the definition of Dmax. Then we swap. We add a supimum over px instead of max x. In particular, in this case, notice that this expression actually has nothing to do with px. We can just add px on the denominator and numerator. So this is greater or larger than the partial smooth Dmax. because of the definition. And now for the asymptotic part, or the first order part, we are able to show that okay, for the achievability bound, we're able to show that it's a smaller, you need at most capacity amount of bits. Firstly, you apply the previous result for n copies of W, and you just plug it in, and you have the first line. Then you convert the whole thing to the spectrum divergence. There's the relationship between spectrum divergence and the max divergence. And yes, and we used equation 9, inequality 9, which is a modified version of the theorem 9 from this paper, slightly modified. Then, okay. Then we use the, I think this is called quasi-convexity of the spectrum divergence. And then one can, okay, wait, okay. And here we chose a specific, because this works for all QY. Is it because it's smaller or equal to an infinite often of all QYs? We chose a very specific QY and plug it in. And where QY is the average over all input types, the average of the output distribution with respect to all input types. And you directly plug in QY, you have this part. And so it's just directly plug in. Then we can, instead of consider all the types lambda, we can just pick a specific lambda, which is the type of the sequence X. That when you do the supremum or sequence X, we just replace that lambda by the type of sequence X, and then that would give that additional term, that is probability of sequence the type respect of the sequence X happening, take a log, and in this case, the first part, then we expand it. We expand the first part. That is the expansion of the spectrum divergence, where V is the divergence variance of the information divergence. So then, okay. Then if you look at the first part, we have sum over I, that's n copies of them, but X is here. So this is an equivalent just by counting. You can recover the frequency of fx. So by counting, we have the first part being the mutual information, and we just copy down the second part. And all the terms besides this term will tend to 0, and this term is upper bounded by the capacity. Okay, so that is the proof of the first order result. As for the converse part, we start with the previous one-shot result and plug in the n-fold of W. Then again, we convert it to the spectrum divergence using a different lemma. And we're okay, yes, lemma 7 is here. Then we do have an infimum over QY. Here, yes. And this can be thrown away by adding additional term. And without QY, just by the famous information spectrum method, we know the first part will tend to the capacity of the channel. And the second part will tend to 0, which is kind of straightforward here. So combining the two previous results, we know the first order cost for channel simulation is capacity of the channel. So as a summary, we give the upper and lower bound, one-shot upper and lower bound to the channel simulation cost in terms of the smooth max information, smooth max mutual information of the channel. The achievability part is a result of the convex space lemma. And the converse part is a result of a lockability and data processing inequality of Imax, among other things. So we know asymptotically the cost coincide with the capacity of the channel. So, and this implies the channel interconversion on the first order. That's the technical part I talked about. There are other things I think that's noteworthy, but I haven't talked about them. That is, we also know the second order behave like this, and okay, actually we know the third order behave like this when the channel divergence, okay, this is type 1, this should be larger than 0. When the channel dispersion is greater than 0, and when it is 0, we have a simpler form. So this is interesting because this implies that channel interconversion won't work on second order. Okay, that's all for my talk. Any questions?
Okay, thank you for the talk. Is there any question or comment?
Hello, Hao-Chun?
Yes, yes.
Please, Hao-Chun.
Hi, Michael. Thank you for this nice talk. Nice to see you again. Okay, so I have two questions. The first one is that, do you know the first order of simulation of broadcast channel without degradability? Without, because in your talk, I remember that you consider degradable broadcast channel, right?
Actually, we consider.
Oh no.
We consider general broadcast.
General, okay.
Yeah, that is only an example.
Oh, okay, that's interesting because in the
this works for all broadcast channels.
Not just a
for all 1K broadcast channel, you have one sender.
Yeah, we can just consider two binary case, R1 and R2 case, but here in this formulation, it seems that it's a degraded broadcast channel, right? But your result actually beyond that.
The examples, numerical result examples are degraded broadcast channel.
Okay, but your result extend to the non-degraded one.
Actually, we started with non-degraded one. We just finally use a degraded broadcast channel for numerics. Okay.
So my question is that in broadcast channel coding, not simulation, broadcast channel coding, I think the first order, the optimal rate region is unknown, right?
Yes.
So
we don't know how to actually. That's why it's hard to say that. But actually, we know the interconversion would work.
Okay, that's interesting.
So hi, Hao-Chun.
Yeah.
So Michael didn't want to make our result look too interesting, so he didn't mention it. But actually, the interesting thing is that in simulation, we have a nice closed form expression for the region, which we don't know
for channel coding.
Yeah, for the communication tone.
Wow, that's very interesting.
Communication?
Yeah. Okay. My second question is that you use the trace distance partial smooth Dmax, and you relate it to back to the information divergence. Does that hold for the quantum case as well? I saw in Marco's paper, the partially smooth information measures, there's a relation between this smooth Dmax in trace distance to the information spectrum divergence.
Oh, that part.
Yeah.
That a lot of inequalities that we used actually they're from the quantum case. They also work in quantum case, including the partial smooth Imax and its relationship to
information.
Those
spectrum.
Dmax and ds.
Okay. Because for this trace distance smoothed quantity, it probably not an SDP. If you use purified distance as smoothing, for smoothing, then it's an SDP quantity. But for trace distance smooth quantity, probably I'm not sure, but probably it's not an SDP. So it's difficult to compute this Imax trace distance smooth quantity. It will be good to translate to other SDP quantities like information spectrum divergence or hypothesis testing divergence. So
I'm not sure of everything, but some of them will definitely work.
Okay.
Then at a lot of situations, you need to consider swapping the total variational distance to something other than a trace distance.
Okay, that's interesting. Okay, thank you.
It actually depends on how you prove those lemmas.
Yeah, that's very tricky.
In classroom cases are particularly easier to prove those lemmas.
Yes. But I'm not sure for the quantum case. Do we have those nice relations between those quantities? I'm not sure. So that's why I'm asking. Yeah, so maybe you already have some results. Okay, let's talk at some point. Thank you very much.
Thanks.
Okay, other question or comment? So I have one question or comment. So in your initial part, you please back to the slide connection to some other works. This one contains some equation one. Yes. In this slide, you consider second problem. So you consider one-shot bound on the channel coding. So in this case, you consider ratio R epsilon as M epsilon. That ratio is definitely smaller than 1. Did you consider that ratio in this talk, in this research, in your research? A simple behavior of this ratio.
Do you mean to ask, did I consider a situation that I replaced this perfect channel 1 with some other channel?
I'm asking this ratio, a simple behavior of ratio, R epsilon and M epsilon. So you mentioned that this one is definitely smaller than 1. Of course, this is correct, but
they tend to actually if we consider situation with as many copies of W
yes, of course,
as possible, then asymptotically, this term will tend to 1.
1.
I believe so. This is like
I think this is 0. This is 0.
This tend to 0. I thought for first order channel 1. Let's put first order channel conversion.
First order is the same, but the second order is completely different. So I consider that problem in the case of entanglement distillation and data compression. Not channel coding, but similar problem. So the channel entanglement distillation and dilution, this is somehow dual problem. And also random number generation and data compression can be considered dual problem. In that problem, this kind of ratio should equal to 0 when epsilon equal to 0. I consider that problem. So because this kind of, if you consider second order expansion, that second order coefficient is completely opposite in that problem. First order is the same, but the second order coefficient is completely opposite.
Yes, the second order term has opposite. So opposite. When you do the one minus another, they actually add together.
Yes, so if epsilon and another epsilon plus equal to 1, maybe okay. But now you are consider
what I was thinking about.
Zero, so
what I was thinking about does it still tend to 0 even if we let the number of copies of W tends to infinity?
Yeah, I think so. If both epsilon go to 0, this is 0, I think.
But I thought it's like you need to consider
both epsilon, upper epsilon and second epsilon, the sum of both epsilon equals to 1. So in that case, I think this is 1.
How about for fixed epsilon?
Fixed epsilon somehow maybe if n go to infinity, maybe 0. because second order is different. So
That would be very kind of surprising to me. I'm not sure about it. I
I
think
already discussed that problem in several papers, so you can read my paper. I can send it to you.
it is very interesting.
Or maybe I can make a comment. So I think it's just a different formulation. Michael, we can look at the paper by Professor Masahito Hayashi, and then it's a slightly different formulation, and in that case, yeah, you can show the irreversibility, but
Yes,
it also follows from our arguments. Yeah.
Okay. Any other questions?
Other question or comment?
Very interesting results.
Lika, okay, please.
So, yeah, I'm interested if it sheds some light to the quantum case.
Actually, the entirety of this project started from the project of quantum channel simulation. But there are just some other difficulties we encountered in that project. So we figured we should deal with the classical one first. So yes, a lot of the methods used here are either inspired by some quantum literature, or they are just analogy to quantum results, especially those inequalities.
Okay, so sorry, maybe we already discussed enough time. So now I want to close this session. So thank you very much. So I already opened